Alright, hey guys, so in this video I'm going to do the second half of the Unit 5 review number 2. So for question 10, we want to classify each of these statements as true or false. So the first one, if we've got an isosceles trapezoid, does that mean that there are two pairs of adjacent angles that are congruent? And the answer here is yes, right? This is true, because in an isosceles trapezoid you have those two bottom base angles that are congruent and the two top base angles that are congruent. And these are adjacent to each other, and so are these. So this first one is true. And then for a kite, both diagonals are angle bisectors. This one's false. Only one of the diagonals is an angle bisector. So if you think of your kite as sort of this up and down this way, this diagonal will be an angle bisector, but this one will not. So this is false. If something's a square, does it have to be an isosceles trapezoid? And here the answer is no, because remember we defined a trapezoid to have exactly one pair of opposite sides parallel. And then for it to be isosceles, the non-parallel sides have to be congruent. And in a square, both pairs of opposite sides are parallel. So that is false. For D, if diagonals are perpendicular bisectors of each other, then that figure has to be a square. This one is also false. It might be a square, but the most specific thing we can guarantee the figure has to be here is it has to be a rhombus. So in a rhombus, if the diagonals are perpendicular bisectors of each other, it has to be a rhombus. It might be a square, but it doesn't have to be. And then here, if something's a rectangle, then the diagonals are congruent, and that is true, right? If we know it's a rectangle, then we know that the diagonals are congruent. That is one of the properties of all rectangles. All right, and for question 11, we've got a rhombus, so we know all of the sides are congruent, and we also know that the diagonals are perpendicular bisectors of each other. So I know that this is a right angle right here, and I know that this is half of the shorter diagonal, and this is half of the longer diagonal. And now, because I have a right triangle here, I can go ahead and use the Pythagorean theorem to figure out the length of x, and then multiply that by 4 to get the whole perimeter. For number 12, I've got a square, so I've got a right angle here, and I'm connecting these midpoints, so if each side length is 18, half of that will be 9 and 9, and then, again, Pythagorean theorem will get us that x is the square root of 162, and that can be broken down into 81 times 2. And remember, I chose 81 because I'm looking for the largest perfect square factor, and 81 is a perfect square. So the square root of 81 will give me 9, square root of 2. And number 13, I accidentally duplicated this. This was actually on review number 1, so we're not going to talk about that. All right, and then for 14, we need to explain why this figure must be a rhombus. So we're starting off with the EFGH is a square. So I know that these are right angles here, here. So it has all 4 right angles. All 4 sides are congruent. And we're given that these segments as marked on the picture are congruent. We also know that the whole thing is a square. So we know that each side is congruent. So I can get these congruent to each other by segment subtraction. And now I have all of these triangles on the outside are congruent to one another. So these sides are all congruent by CPCTC. And therefore that's a rhombus. So I'm going to write that up and I'll be right back. So here's what that would look like. And remember, this is one that's an explain question, not a prove question. So if you're just asked to explain, it's a lot less formal than it would be if there were a proof. Right, so for part B, I went ahead and just labeled some of the angles up here. So I know these triangles are congruent, this little one here and this little one here. They're also congruent with the ones at the top, but I don't actually need those. So I know that x plus y plus 90 has to equal 180 from the angle sum of a triangle. So that's this first equation down here. And that's going to allow me to figure out that x plus y have to be 90. Now I can't figure out what either x or y are, but I don't actually need that. Because what I need right here is, I know that y plus x plus w is that straight angle right there, so that equals 180. So I know that x plus y plus w is 180. Well, I just figured out that x plus y is 90, so I can substitute here, I can substitute 90 for this x plus y. And that gets me that w has to be 90 degrees. And that makes EFGH a square because a rhombus with a right angle is a square. All right, and here's 15. You can You don't have to graph this if you don't want to. I find it helpful to have it graphed so you can just count to find the slope so you're not making any silly arithmetic mistakes when you're adding or subtracting. So we're going to make the same chart that I've made for all of these. I'm going to list the side, and then I'm going to list the slope and length of each of those sides. In this case, you actually do need both, right? We need the length to prove that it's a rhombus because we have to prove that all four sides are congruent. And then we need the slopes to show that there aren't any right angles. So we get all side lengths are equal, which makes all the sides congruent. Therefore, it's a rhombus. And then there are no negative reciprocal slopes, so there are no right angles, which means LMNP is not a square. All right, so for 16, I know there's more than one way to do this. I actually have written up 2 different solutions myself. So I'm going to show you the one that actually took fewer steps. So we're given that ABCD is a parallelogram. So we get a lot of information with this. The things we're going to need that are true about a parallelogram are that the opposite angles, both pairs of opposite angles are congruent. And we also need that both pairs of opposite sides are congruent. Those are the only facts we're actually going to need for the proof that I'm going to write. So I know that angle D is congruent to angle B. I know that angle DAB up here and angle DCB down here are also congruent because both pairs of opposite sides, or both pairs of opposite angles in a parallelogram are congruent. And then I know I'm given that these perpendiculars, so I know that angle 3 and angle 4 are congruent. So I'm going to get angle 1 congruent to angle 2 by angle subtraction. And now if you're looking at this triangle right here, triangle AFD and triangle CEB. And I'm just going to redraw these down here so that we can see what's happening. So I have a triangle AFD and I have triangle CEB. So I've got this angle congruent to this angle. I have this angle congruent to this angle. And I also, I guess, no, I don't know that. Okay. And then I thought I just found another way, but I did not. So, and then we also have these opposite sides congruent up here. I know that AD and BC are congruent because opposite sides of a parallelogram are congruent. So I get these 2 triangles congruent by angle side angle. And now I get all of their corresponding parts congruent. So let me get some of this out of the way here. So now I know, so my goal here, by the way, is I've highlighted the segments that I'm trying to prove are congruent, and I've noticed that they're segments of these little triangles right here. So I'm going to try to prove this little triangle congruent to this little triangle. So now I have DF right here. I have this segment congruent to this segment by corresponding parts. I have right angles right here and here at 5 and 6, and then angle D and angle B are congruent. So now this little triangle, HFD, and triangle GEB are congruent by angle side. And that's going to get me BG congruent to HD. So there's a lot going on in this picture. This is a pretty tough proof because of the fact that there's so many extra things and so many lines in this picture and so many extra triangles. So part of the task here, and a big part of the task, is just figuring out which triangles to prove congruent. And so my suggestion is if you're ever stuck on a proof and really have no idea what to do, work backwards. Highlight the things you're trying to prove are congruent, and then think, okay, well, if I need HD congruent to BG, then I need this triangle congruent to this triangle. Well, how can I get that? And kind of work your way backwards. So, you would recognize that you have angle 5 congruent to angle 6, and the angle B congruent to angle D. So if you could get either HF congruent to EG, or DF congruent to EB. And once you recognize, so for example, if you wanted to try to prove HF congruent to EG, you would want to try to prove this triangle right here congruent to this triangle right here. And I think you could probably do that. So that may be another option that you would have. And if you want to try to prove DF congruent to EB, that would be these bigger triangles right here. And these are harder to see because this triangle is really composed of 2 other smaller triangles in the original picture, which is why drawing them separate might be really helpful as well. So that's my hint and tip for what it would like to kind of work backwards from what you're trying to prove and work up from there. So I'm going to write up this proof and I will be right back. So here's what that will look like if you write it up. I know some of this is a little small. That's the only way I could get it to fit a full page. So I'm going to go ahead and zoom in a little bit, but if you need to pause the video at any point in time, go ahead and do that. So I'm going to make this a little bigger so that you can read it. But here it is with the whole picture. Maybe. There we go. So let me make that just a little bit bigger. Okay. So there it is in all its glory. And like I said, I know there's another way you can do this proof. So if you did it a different way, that's probably okay as well.